Like I said, this is just the questions. Do you want me to review the beforehand, or you want to just jump in here and see how you do? We'll just start with the questions, I guess.
Well, with the questions, they're not in our practice book, right? They're just
Yeah,
you've got them.
yeah, yeah. This is in the section following the explanation.
Okay.
So there's the question. What is meant by the term MMIC? I don't know how you pronounce that. Multi-mode integrated circuit, monolithic microwave integrated circuit, metal monolayer integrated circuit, mode modulated integrated circuit. And
Microwave something.
Yeah, I agree.
yeah, I was going to say that's the key there is the microwave.
Yeah. Don't put any metal in there.
Okay. All right. Which of the following is an advantage of CMOS integrated circuits compared to TTL circuits? And this goes back. Low power consumption, high power handling capabilities, better suited for RF amplification, better suited for power supply regulation. And if you remember, CMOS, although it's used for a lot of things, it's primarily used in digital logic. But that don't really fit in here, but I mean, that would kind of throw out power supplies and RF amplification. I don't remember what those are called, those high power CMOS.
It's a
It's a yay, wake up, John. Yay. Okay. What kind of device is an integrated circuit operational amplifier? What kind of device is an integrated circuit operational amplifier? Digital, MMIC, programmable logic, analog. And it's kind of a simple answer. I know. When I reviewed this, I just knew I had to say back in the day the integrated the operational op amps I first worked with were actually tubes. There's two tubes. Little summing.
MUA 741.
Yeah, I don't know if they put them on planes. That was a bunch of knobs and stuff. Anyways, so an op amp, if you're it's one of those catchphrases, I guess. If you knew what it was, the answer would be obvious. It's an
Well, you could look at it. It says it is a amplifier.
yeah, there you go.
Digital doesn't amplifier. Digital doesn't amplify. Analog does.
Right. So it's D. It's an analog device. They're beautiful. They slowly replaced a lot of different amplifiers and filter circuits because they're so universal. Once they made them ICs. Which of the following describes the function of a two-input AND gate? Output is high when either or both inputs are low. Output is high only when both inputs are high. Output is low when either or both inputs are high. Output is low only when both inputs are high.
Bravo.
Yay, thank you. Bravo it is. The basic AND gate, which you rarely use, but now this is one I can't remember the write-up. How many states does a 3-bit binary counter have? 3,
2 cubed.
6, 8, 16.
2 cubed. 2
Three.
to the third power.
3. Yeah, 2 to the third power. There you go. which is,
8.
yes, you
Yep.
got it. Yeah. So I don't know if
Charlie.
I covered that in the text, but yeah, the number, just raise it to that power, raise 2 to the power of the number of bits, and you'll have the states.
It's in the book somewhere.
Is it? Okay.
Yeah, it's in there somewhere.
Charlie. What is a shift register? A clocked array of circuits that passes data in steps along the array. An array of operational amplifiers used for tri-state arithmetic operations. A digital mixer and analog mixer.
A.
Yes. If you know what yeah, the clocked circuits, shift registers. They're actually can be used for um, generating waveforms too by putting the pattern in the shift register. Okay, so much for the questions. Micropot. Let me goof around here a minute. My little displays in the way of reading. Microprocessors and related components. Memory. Microprocessors are microcontroller ICs that are capable of performing millions of computational instructions per second. Millions. Programs must be stored in memory so the microprocessor can read the instructions and store the data too. Volatile memory loses data when the power is removed. Non-volatile memory stores data permanently even without power. Random access memory can be read from or written to. Read-only memory stores data permanently and cannot be changed. I don't know. That used to be a big deal. I don't know if it is anymore. Microprocessors communicate through data interfaces. 2 types exist, serial and parallel. Serial transfers 1 bit of data in each transfer operation. Parallel transfers multiple bits in each operation. And there's a picture of a byte, which is 8 bits. 1, 2, 3, 4, 5, 6, 7, 8. 1 bit. And that was that. Amateur equipment uses 2 types of devices for information visual, for information visibility, indicators and displays. Indicators present an on-off information visually by the presence or absence of color or light. Common indicators, incandescent light bulbs and light-emitting diodes. Displays presents text or graphics information in a visual form. Whoop. LEDs have largely replaced incandescent lamp bulbs in amateur equipment. Last longer, can be turned on and off more quickly, use less power, generate less heat. The transformation is almost over. Available in many colors, made from special types of semiconductor material that emit light when the PN junction is forward biased. Notice that. Now this one, liquid crystal displays are on their way out too, but the most common type of display, been around since the beginning of the 70s, created by sandwiching liquid crystal material between glass panels. A pattern of electrodes is printed on a thin film on the front panel with a single electrode covering the rear. Voltage applied to the front panel causes the crystals to twist in a configuration that blocks light. LCDs require ambient or backlighting light source behind the crystal layer, since the crystal layer does not generate light on its own. Compared to LCDs, LEDs have higher contrast where there is high ambient light. Okay.
I thought it was the opposite.
I know when I read that, it was just confused me too.
Just read that yesterday. I think that's backwards. That LCDs have better contrast. I could have sworn that's what I read yesterday.
Clearly, and you just don't see the LCDs. They're not used much anymore.
Yeah, because they're more expensive, but they're much better quality. You don't have the viewing angle issue.
Yeah, that's true.
You can lay on the floor, your kids can lay on the floor and watch TV and it doesn't turn black, but they're more expensive.
Yeah, there's other problems too with them. They don't, is it the LCDs don't like cold very well either. They change slower. Well, whatever. The question on the same subject made more sense when I went through the questions than that statement back there. How is an LED biased when emitting light? In the tunnel effect region, at the Zener voltage, reverse bias, forward bias.
Oh, it's either forward or reverse.
Yeah, and I could back up 4 slides and the answer is there. It is forward. That's where you got enough power going through it to light up something. Reverse, they are LEDs. I mean, they are diodes. So if you reverse bias, not much current flows. You want them forward biased. How does a liquid crystal display compare to an LED? Higher contrast and high ambient lighting, wider dynamic range, higher power consumption, shorter lifetime.
I think it's A.
Yeah, I think so too.
That means that other one was wrong.
I know. That's what I said.
I'm positive. I just read that yesterday.
Well, I could go back and I think it's just the way the sentence, you know, it didn't read well. When you read it out loud, you're like, what? Let's go back as long as we got a minute here, because that's the end of the chapter and the end of my whole
I'm
thing.
positive it said that in the book, as I just read it last night.
Ambient light.
Oh, John, you have another slideshow to go.
I do.
Yeah,
Oh,
part 3.
part 3, huh? Oh, well, I'll have to go find it, Wes.
Practical circuits, power supplies.
Hmm.
I can step in if you like.
Yeah, page 432 says LCDs have higher contrast and high ambient lighting.
Huh. Okay. Chapter 4, part 1. 2. Huh. Hmm. I'll be darned.
You see part 3, John, or not?
No, I don't know where it is.
Okay.
Oh, where to go here, class. Chapter 4 only. There it is, part 3. Ta-da!
Okay.
That was in 24. All right, I'll be cold turkey here.
What are you guys doing? What are you guys doing? Oh, what are you doing over there?
Okay, this will be fun. Nope.
Psst.
There. That look right?
Yep.
Rectifiers. Amateur radio electronic equipment requires DC power, so a power supply is required to run it from household AC power. Most amateur equipment uses DC power at 13.8 volts, chosen to be compatible with vehicle power systems. as you'll notice, 13.8 isn't 12, but that's what we run. Power supplies have three basic parts: input transformer, rectifier, filter regulator, output circuit. So they threw the filter in. All right, you can do that. And here's some pictures of them. Okay, rectifier. These are classic half-wave rectifier, which you don't see much anymore. And then you have the push-pull type full-wave rectifier. And so the half-wave was real popular at one time when rectifiers were expensive, but boy, they are cheap now. Full-wave rectifier converts the entire waveform. This is really two half-wave rectifiers operating in alternate half cycles. Requires that the transformer be center tapped to provide a return path for current flowing to the load. Okay, well, let's see if they get to the more common. Nope, they don't. The advantage of full wave rectifier is that the output is produced during the entire cycle, as you could see. The output from a full wave rectifier is a series of pulses at twice the frequency of the input voltage. And there's the one I was looking for, a full wave bridge, which is really common. You can buy them all in one module anymore. And as you can see, you get lots of little humps there.
Just as an aside, which doesn't have a lot to do with what you're saying, but I had a rectifier in a space heater with an electronic control unit, and one of the diodes, which is a 4004, had died. And I went to Micro Center. I had a bunch of them here, but I didn't know where they were. So I went to the Micro Center to get one. They didn't sell it in one. You had to buy a package of 10. Okay, so I can do that. They usually run around 30 cents a piece. For the 10, it was $15.99.
Wow.
Just blew me right out of the saddle. I came home and found.
Oh, you didn't buy them?
Yeah, no, I did not buy it. I went home and I found it. So, but those are
Wow.
using power supplies, and I had a power supply problem.
Mm-hmm. Yeah. How many amps was that?
Just 1 amp.
1 amp. Okay.
It's just a control for the controller. It got an infrared remote controller, and then gets into the electronics.
Hi, Gabriel. How are you?
Oh,
I'm getting along.
hey, Marv. I don't know how to do that. It must be a way. Anyways, so that's a full wave bridge, which is pretty common now. And this shows you in slow motion how they work by these diodes directing the current to only flow one way. And it's pretty another type of full wave rectifier. This circuit adds 2 diodes, a total of 4, but eliminates the need for a center tap winding. And sometimes you don't need any winding at all. Rectifiers' output pulses of DC current don't provide a stable voltage for direct use by electronic circuits. Those little bumps, you'll hear them. The variation in output voltage is called ripple. Pulses must be smoothed out by a filter network, consists of capacitors and inductors. Okay. Most common way to reduce ripple is a filter capacitor or capacitor input filter. Okay. Older high voltage circuits may use choke inductors. Power supply safety. Fuses in the primary are used to protect against short circuits or excessive current loads. That's in the primary. Bleeder resistors discharge stored energy when the power supply is turned off. Working on power supplies, wait for the bleeder resistor to discharge energy, even if it is unplugged. Yeah, I got used to working with low power, 12 volts and below, and then that can make you a little sloppy and you can get hurt with the high voltage. AC input is first rectified and filtered. Transistor switch pulses wait a minute. What we're talking about here is a switching power supply. So first you rectify it and turn it into DC, then you turn it up, then you generate a high frequency pulse, like 20 kHz here or more, and that'll allow you to use a smaller transformer. High frequency enables the power supply to quickly change to current demands and means that small, lightweight inductors and capacitors can be used to filter the output. And that's, boy, they're so much lighter than the old ones. This block diagram illustrates the basic operation of a switch mode power supply. The power switching transistors are turned on and off at a very high rate so that smaller transformers and filter components can be used. Filter capacitors, power switching, high frequency, full wave rectifier, capacitors output, switching control. Yeah, they usually have this feedback circuit to keep the voltage constant, I believe. They are nice, though. Boy, those old transformers, they went from like 15 pounds down to about 2. AC input is first rectified and filtered. Transistor switch then supplies current pulses to a small inductor or transformer, which transfers the energy into another filter capacitor that smooths the pulses back out again. The high frequency of the pulses means that the supply can react quickly to changing current demands. The high frequency also means that small, lightweight inductors and capacitors can be used to smooth the pulses. Oh, that's it. Here we go with the questions. What is the function of a power supply bleeder resistor? It acts as a fuse for excess voltage. It discharges the filter capacitors when the power is removed. It removes shock hazards from the induction coils. It eliminates the ground loop current. So these, since you're dealing with a lot of power with the power supply, that's the word power, so you end up needing some really big capacitors to smooth it out. Unlike when you're at RF frequencies, few microfarads will do it. But these guys usually run 20 to 50 microfarads. They're pretty big capacitors. So, you guys want the answer?
With the one that has the word capacitors.
How about B?
One that has capacitor in it? Okay, well, you got to discharge it. That's the whole thing. You want to discharge it. And, when they said that, depends on the voltage. If you're working with tubes, the voltage is like several hundred volts, so that'll really knock your socks off. But if you're working with a 5-volt logic, yeah. Which of the following components are used in a power supply filter network? The filter network: diodes, transformers, and transducers, capacitors and inductors. All these are correct. Now this is the filter network. So, come on.
Capacitors and inductors.
Yeah, it's Charlie. Charlie it is. Which type of rectifier uses 2 diodes and a center tap transformer? Full wave bridge, half wave synchronous. Well,
It's either A or B.
yeah. And I think the bridge is that little square thing.
Yeah, bridge uses 4.
Yeah, so A is the answer there. Yeah. That's the bridge part. What is characteristic of a half-wave rectifier in a power supply? Only one diode is required. The ripple frequency is twice that of the full-wave rectifier. More current can be drawn from a half-wave rectifier. The output voltage is 2 times the peak input voltage. Well, yeah, remember I said that they don't use them much anymore because the diodes are so cheap. But back in the day, well, at one point the diode was a tube. So it was a big deal how many diodes you had. So this is an alpha. Only one diode is required for a half-wave rectifier. And that's the reason. What portion of an AC cycle is converted to DC by a half-wave rectifier? Okay, half-wave. So, you know, a whole wave is 360 degrees. So there you go.
B.
There is. Answer is Baker. 160, 180 degrees. You just get one hump instead of two. So what portion of the AC cycle is converted to DC by a full wave rectifier? 90, 180, 370, 360 degrees.
Must be 360.
Yay. We got precipitation there. What is the output waveform of an unfiltered full wave rectifier connected to a resistive load? Full wave, unfiltered. A series of DC pulses at twice the frequency of the AC input, a series of DC pulses at the same frequency as the AC input, a sine wave at half the frequency of the AC input, a steady DC voltage. Wow. So, I mean, there's one answer that just jumps out at you there, don't it? The full wave, you're getting all the humps. And so you're so it's about the frequency here. Boy, wish I could back up and show you the picture.
It's A.
Yeah, it's twice A, because you take each, the positive and the negative part of the sine wave, and you make them all positive. You end up with 2 pulses. So it's twice the frequency. Which of the following is characteristic of a switch mode power supply as compared to a linear power supply? Faster switching time makes higher output voltage possible. Fewer circuit components are required. High frequency operation allows the use of smaller components, inherently more stable. Well,
Definitely C.
yeah, it's a Charlie. Allows use of smaller components. Yay.
And cheaper.
Nah, there's more circuits, but I don't know. 2 battery types. Oh, batteries and chargers. 2 battery types, primary and secondary. Primary, disposable, discarded after discharging. Battery chemistry, carbon, zinc, alkaline, silver, nickel. Preferred to secondary batteries for emergency operation because AC power may not be available for charging. Okay. Secondary can be recharged, reused many times. Battery chemistry, and this goes back, nickel cadmium, nickel metal hydride, lithium ion, lead acid. Wow, and here's whoop. Let's see everything. But this is the interesting part, I think, is the amount of current in them, or amount of what do they call it? Milliamp hours. Quite a variation there. Um, nickel metal hydride was really popular with the rechargeables. Storage batteries, larger secondary batteries. What are we going to learn here? Whoa, slow computer there. Used for emergency portable power to replace power supplies operating from AC. Oops, wrong. I'll get it figured out here. Battery chemistry, lead acid, liquid electrolyte, gel electrolyte, gel cells. Rated as 12-volt batteries, but are actually 13.8 when they're fully charged. Lead acid batteries can produce useful power down to 10.5. Discharging below minimum voltage will reduce battery life. And my only comment there is, what's really cool is if you let it go all the way down to 0 and hold it there for a couple of days, you'll never use that battery again. Limiting amount of current drawn keeps the battery cool and extends life. Okay. Some battery types, nickel cads, are designed to have low internal resistance to supply high discharge currents. Batteries slowly lose charge when not in use, called self-discharge. Minimized by keeping battery cool, dry, but avoid freezing. Expanding water can crack the cases or damage electrodes. Yeah, it's that time I got to get my batteries out of the garage, my rechargeables. Solar power, voltaic of sunlight to electricity. Solar panel cells are a special type of diode, silicon PN. Isn't that interesting how everything goes back to a PN junction? In solar cells, photons are absorbed by electrons, giving them enough energy to travel across the PN junction and create a DC current flow. The forward voltage created, approximately 0.5 volts, is called open circuit voltage. Wind solar power system, I did a double click there, guys. Wind solar power systems require substantial energy storage. When connecting a solar panel to a lithium ion phosphate battery, use a charge controller to avoid overcharging the battery. Okay, that's one thing I keep getting warned about. Solar connections are made through a series connected diode to prevent battery from discharging back through the panel during periods of low illumination. Yeah, I learned that the hard way. I was charging and I got a cheap solar panel. And yeah, if I left it just sit there, it would discharge it. So I had to put some diodes in series. Solar panels and solar cells are made of silicon PN junctions that are exposed to sunlight and arranged in a series parallel configuration. Oh, that's all we get. Practice questions. In what configuration are the individual cells in a solar panel connected together? Series parallel, shunt, bypass, full wave bridge.
Alpha.
I think the only one that makes sense is A. Yeah, it is A. Shunt, bypass, full wave bridge. Yeah, they're trying to confuse the word diode with power supplies lecture, I think. What is the approximate open circuit voltage from a fully illuminated silicon photoelectric cell? 0.02, 0.5, 0.2, 1.38. And like we were saying, some of this you just got to memorize, you know. It's, I guess, I mean, we were taught that forward drop was 0.7, but here we got a little bit different number. And it's a half volt guy, 0.5 B. half volt, which I guess is similar to the forward bias voltage, but the forward bias is 0.7. Why should a series diode be connected between a solar panel and the solar storage battery that is being charged by the panel? To prevent overload by regulating the charging voltage, to prevent discharge of the battery through the panel during times of low or no illumination, to limit the current flowing from the panel to a safe value, to limit the current flowing to a safe value. I guess you'd blow out the diode or something. To prevent damage to the battery due to excessive voltage at high illumination levels. Well, that'd be a good idea, but the answer is
Bravo.
so. Yeah, it's like the solar cell becomes a load, and you don't want that battery you just charged to discharge back through the load, because the solar cells aren't really perfect diodes. They're just something that generates electricity for us. What precautions should be taken when connecting a solar panel to a lithium iron phosphate battery? A LiPo, I think is what we call them now, don't we? Ground the solar panel outer metal framework. Ensure the battery is placed terminals up. A series resistor must be in place. The solar panel must have a charge controller.
Delta.
I know
Yeah.
I have two charge controllers on my my solar panels on the RV, so I say D.
Okay. Yeah, I know I got to get a good one. A guy gave me one for a lead acid, and I've got a lithium no, the um, sodium. So I got to get a different charge controller.
Yep.
Okay, but you got to have one, and that was the only answer that was even close to right. What is the minimum allowable discharge voltage for maximum life of a standard 12-volt lead acid battery? I almost went when I
Charlie.
yeah, it is Charlie, and that's a little lower than I like to go, actually, 10.5.
Yeah, I always used to keep it at 11.
Yeah, I think a lot of um, car computers cut out in the 11-volt area. Of course, there when you kick on the starter, it's going to drop some more, I guess. But yeah, Charlie, it is. What is an advantage of batteries with low internal resistance? Long life, high discharge current, high voltage, rapid recharge.
Rapid recharge.
They mentioned this, and that was kind of a surprise to me, but no, it's the high discharge current, I'm pretty sure. Yeah, I guess, I mean, resistance turns into heat when you start pulling current through it. So I guess a high discharge current would uh, overheat the battery.
Hmm.
So you don't want a high discharge current. Connector terminology. Pins. Contacts that extend out from the connector body. Male. Sockets allow recessed contacts. Female. Keyed connectors, specially shaped bodies or inserts to prevent damage from connecting incorrectly. Plugs, connectors installed on ends of cables, jacks, receptacles, connectors installed on equipment. Adapters make connections between two different connector styles. Splitters divide signals between two connectors. Okay. So here's some pictures of them, guys and neighbors. Any of them look familiar? The big thing I've seen change is they're really going to crimp for as much as possible, crimping things now instead of soldering. And there's your terminal strips. And the power pole's kind of new too. Power connectors. Anderson power pole connectors have become standard used by ARS. Anderson connectors are sexless by standardizing on a single style. Equipment can be easily shared or replaced. It is nice to have the same connector on everything. It sure is.
It
Because,
costs more though. It
yeah,
costs a lot more.
they do.
Oh, yeah. I just went through that with my new power supply.
Oh, did you buy the parts to do your own or?
Well, I took my mobile rig out of my car, an ICOM 7100, and with the install, they chopped off the end, so I didn't have any connectors. And I went to Wow Electronics here in East Detroit, and they had a lot of, they could do it, but it would have been a lot more money for them to put power pole connectors on the ends instead of the uh, what do you call the little round ones?
I
Not the
can't remember
fork, but the
what they
circle, not the fork, but the little circles,
uh-huh.
rings. Yeah.
Oh, yeah, I somehow acquired the crimping tool for the Anderson power pole. So
Those crimping tools are really expensive too. I
yeah,
looked
it
in.
was really
The good
expensive.
ones are like $100.
No, this wasn't that much, but it was more than 10. And yeah, I don't remember how much a single one cost because I usually would buy packets of, a dozen of them or so. Um,
Well, the reason I mentioned that diode and they're mentioning that power poles are expensive now. All the tariffs are kicking in, and that's the reason everything's going up.
yeah, most electronics is offshore, really. Um, the thing I ran into with power poles that kind of I don't like, but you got to live with it, is you don't buy them by the size of wire you're using. I can't remember, but you don't buy it for like a 10 gauge or 12 gauge wire. You buy it by some kind of size standard, and I can't quite. I think it's by the current, I think. There's one standard, like you were saying, that everybody uses on power supplies and that. Once you got everything converted, it's nice, but yeah, when you get old equipment, that's your first problem is figuring out how to power it. There you go. More connectors. Yep. And there's your mini DIN and the DIN. Those are always fun to solder. And also the type Ds. They seem to be disappearing now, the Ds more so. The DINs are still pretty popular. And the microphone connectors, I don't know where those standards came from. They don't seem to be changing. The nice thing is all these audio connectors are just common across lots of industries, so they're really easy to get a hold of. The phono, some people call them RCA connectors, I believe. Come in 1/4, 1/8 inch, sub-miniature. There's many more than 1/4 and 1/8. I used to think that was the only size audio. I just ran into one the other day that is less than 1/8. Contact at end of plug is the tip. Okay. Connector at the base of the plug is the sleeve. Third contact, if applicable between the tip and the sleeve is the ring, also called the TRS or tip ring sleeve. See, I was afraid of that. They don't have the fourth one. Phono plugs jacks, also called RCA connectors, are used for audio, video, low-level RF, and control signals. They're really pretty good and pretty cheap and easy to work with. But the new headsets where you have a microphone and a right and a left earplug, they end up with a third ring or two rings not just one. And they make converters for those too. Here's some RF connectors. The famous UHF or PL259. They're on the corner there. The F connector, which came out of the TV systems. BNC and BNCN. Oh, SMA, that's what they're saying. SMA, an N, and there's another N, some more VHF all across there. And these are converters like to get from VHF or PO259 to BNC. And these are different converters. And there's some converters to SMA. You go back to World War II, there's even more of them. Oh gosh, on some of the old equipment. Each type of RF connector is specifically made to carry RF signals and preserve the shielding of the coax cable. Adapters are available to connect one style of connector to another. Go. Radio signals require special connectors for use at RF frequencies. Connectors must have about the same impedance as the feed line, or some of the signal will be reflected by the connector. Most common connector is the UHF family. UHF does not refer to ultra-high frequency, which I always thought it did, but okay. UHF connectors are typically used up to 150 megahertz and can handle legal limit transmitter power at HF. UHF connector was nicknamed during an era when UHF meant frequencies over 30 megahertz. Ultra-high frequency refers to frequencies between 300 and 3 gig. Yep, that was the beginning of the radar, World War II, I believe. UHF connector drawbacks: lack of weatherproofing, inconsistent performance above 150 megahertz, limited power handling at higher frequencies. And there's more problems. They are the most common used, though, with ham radio. Type N series connectors address these drawbacks, can be used up to 10 gigahertz. Yeah, maybe. BNC connectors are used for low power, common in handhelds for antennas. Upper limit for low SWR operation is 4 gigs, so they're pretty good. SMA connectors are small threaded connectors designed for miniature coax rated at up to 18 gigahertz, also used for handheld antennas. That's been a big change. They used to all be BNCs, and now they're mostly SMAs. So you need another converter. Digital data is exchanged between computers and radio equipment more than ever before in ham radio, amateur radio, excuse me. D-type connectors are used for RS-232 COM port interfaces. You remember RS-232, anyone? The model number of the D connector specifies the number of circuits and a P or S depending on whether the connector uses pins or sockets. For example, D-type 9-pin connectors referred to as DB9 or DE9 are used for COM ports on PCs. The D refers to the shape. Yay. See, it looks like a D, kind of. You see a lot of 9 pins. Every once in a while, I'll see a 20 pin, but practice questions. What is a typical upper frequency limit for low SWR operation of 50 ohm BNC connectors? Oh, they're going to quiz you on this stuff. BNCs, 50 meg, 500 meg, 4 gig, 40 gig. A hertz, good old hertz. I'll be guessing here. But now
What
this
is
is
BNC?
We just covered it. It's 4 gigs.
Yeah, I think it was. It's pretty good, really, the BNCs. Gosh, we used them in a lot.
BNC?
Yeah, BNC is 4 gig. That's what they're recommending.
But what does BNC stand for?
You got me there.
It's a
Yeah,
couple of guys' names. The first guy's name is Bayonet. I forget the second guy, Bayonet Coates and something. It's three guys' names anyhow.
Oh, so it doesn't, okay, it's just an eponym then.
Yeah.
Pretty old, I think, isn't it? Like the 40s, 50s. They actually made bigger ones too. I don't see them anymore. A moisture resistance R, well, which of the following describes an N connector? A moisture resistance RF connector useful to 10 gigahertz, a small bayonet connector used for data circuits. A low noise filter figure VHF connector, which I don't know if we can cover that, a nickel plated version of the PL259. Well, there's a couple of big clues there. Besides the frequency, because they did mention that. And the first time I used them was for the moisture resistance. They got some nice little O-rings on them, so you don't, the outside moisture can't get to the inside. So the answer is alpha. It's moisture resistance, and they said it's good to 10 gigahertz, where the BNC is only good to 4 gigahertz. What is an SMA connector? And I don't know what it stands for. A type S to type M adapter. Ooh. A small threaded connector suitable for signals up to several gigahertz. Ooh, a connector designed for serial multiple access signals. SMA, huh? A type of push-on connector intended for high voltage applications. Well, let's see. Type S to type M adapter. So I don't know what those two things are. I think they're just making that one up. SMA. Oh, size M adapter. SA. Small threaded connector really rings a bell with me there. A connector design, yeah, serial multiple access SMA signals. You guys must not. I'm having trouble remembering what that is. That
yeah, it's B.
Ethernet, I think. Or is that anyways, a type of push-on connector intended for high voltage applications. And that, no. So the answer is B. The threaded connector. I guess if once you had one in your hands, that would jump out at you. There's none of the other connectors are threaded. They're all twist type.
And just for
Oops.
just for the hell of it, SMA stands for Sub Miniature Version A.
Oh,
Yeah, Sub Miniature Version A. BNC is Bayonet, Neil, and Consulman. It's the three guys that.
where do you get this stuff, Bob?
I use it in the tech class in chapter 4.
Oh,
You know what? It's not that anyone needs to know that, but some people ask, and so I looked it up
oh, okay.
sessions ago.
It's not
Yeah,
in the
actually, I
manual,
put the BNC in the chat a couple minutes ago, but it's like I didn't have no idea about the SMA.
Oh, I see. You do have a chat up there. Oh, wow. Which of these connector types is commonly used for low frequency or DC connections to a transceiver? PL259, BNC, RCA phono, type N. Well, is commonly used for low frequency or DC signal connections.
Yeah, it's probably an RCA.
Yeah, I think so. Because that, yeah, phono, yeah, that's, your old, any audio equipment you have that you used to plug into your TV, they were all RCAs, and that's pretty low frequency. Let's see if The colonel's right. And it is RCA Phono. And that stands for Radio Corporation of America. Basic test equipment, analog and digital meters. Oh boy, here we go. A voltage ohm meter, VOM multimeter is the simplest and very versatile piece of test equipment. Two types, analog and digital. Functions, measures voltage, measures current, measures resistance. Checks continuity, tests diodes, tests transistors, frequency counter, measures capacitance, measures inductance, and interfaces to PCs to record readings. Huh.
That's what I said.
I-
Uh,
I guess if you bought the expensive one, huh?
yeah. The digital will do that. The
Whoops.
analog won't.
Yeah. Well, I got digital ones that won't do any of that, connect to PCs or nothing either, you know. But yeah, most of them are actually digital displays anymore, I think.
Yeah, unless you get a old
Simpson. I got some Simpsons.
I have
Yep.
an old Radio Shack one.
Yeah, that works too, huh? I got more digital ones that die in their old age. Well, let's get going here. Digital multimeters, DMM, offer greater precision than analog meters. And for finding peak or minimum readings, for example, when adjusting or tuning a circuit. What is for that? Experienced hams often prefer analog meter, easier to watch, to just watch the analog meter needle move than the display or digital meter. Oh yeah. And some of it's how the digital meter's set up. Some meters roll better than other in the digital mode. Meters should affect the circuit being meters should affect the circuit being measured to the smallest degree possible. Okay. When measuring voltage, meters should have a high input impedance so it places minimal load on the circuit. Okay. Oscilloscope provides visual display of voltage against time. Display is updated thousands or millions of times per second to give a real-time view of the signal's characteristics, allows for measurement of fast-changing waveforms that can't be measured by other meters. Okay. Signals are connected to the scope through a horizontal and vertical channel amplifiers. Amplifier gain is variable to adjust and vertical sensitivity of the scope's display. Used for monitoring transmitted signals by connecting the attenuated RF output of the transmitter to the vertical channel of the scope. This assists in adjusting keying waveforms, microphone gain, and speech processing. When adjusting keying waveforms, CW transmitter, the operator can see on the scope's display the effects of any adjustments or conditions that might cause distortion or key clicks on the transmitted signal. Whoops. An antenna analyzer contains a CW signal generator, frequency counter, SWR bridge, and an impedance meter. Oh, I'll go get one at break. Connects to the antenna feed line to measure SWR without having to transmit a signal at high power. Measures feed line velocity factor, electrical length, and characteristic impedance, and other parameters. Because they use small signals, accuracy can be affected by strong signals from nearby transmitters. We see that at field day when we set up next to a broadcast tower. Field strength and RF power meters. Other useful tests includes antenna efficiency and radiation pattern measured with a field strength meter. You kind of walk around the transmitter with a field strength meter and plot it out. Field strength meters are often used for comparing relative levels of RF output during antenna and transmitter adjustments. No kidding. Radiation pattern is measured by placing field strength meter in one location and rotating the antenna, or the meter can be carried to different locations to determine the radiation pattern of a fixed antenna. And I've got a cheap field strength meter, and it's just relative. If you get a calibrated field strength meter, you're talking some bucks now. Directional watt meters measure both forward and reflected power, piece of F and piece of R in the line. Okay. Standing wave ratio can be calculated from forward and reflected power measurements. Ooh, they're going to give it to us. Yes, sir. The square root of the P's over F's, one plus one and one minus one. Oh boy. Huh. I wonder if that'll be on the test. We'll find out. Practice questions, and then we can take a break. How's that? What item of test equipment contains horizontal and vertical channel amplifiers? An ohm meter, a signal generator, an ammeter, and oscilloscope. And, you know, just reading it and describing it don't do it justice. You have to really use one of these instruments to really get good with them. It's not like a meter where you just get it on the right range. Although I can blow up a meter pretty good too, if you have it in current mode when you're measuring voltage. Oh, well, I guess we're not going to get an answer here, but the answer is an oscilloscope, D. The D. Horizontal and vertical channel amplifiers. I guess you guys haven't used them much. Which of the following is an advantage of an oscilloscope versus a digital voltmeter? An oscilloscope uses less power. Complex impedances can be easily measured. Greater precision or complex waveforms can be measured. So the power thing is kind of a ruse. I mean, the old ones used to use a lot of power. The oscilloscope was a tube, but they're a complicated piece of machinery. Complex impedances can be easily measured. Luckily, they put the word easy in there because with a lot of work, you can probably measure complex impedances. Greater precision. Now, oscilloscopes are not known for precision. I mean, you can calibrate them and gain precision that way, but out of the box, who would trust them? So the answer is delta. Which of the following is the best instrument to use when checking the keying waveform of a CW transmitter? An oscilloscope, a field strength meter, a side tone monitor, a wave meter. Well, the answer is,
It has to be A. The other ones make no sense.
thank you. Thank you. Yeah, they were talking about that. I guess I read through that pretty fast, and you'd have to really want to do it. What signal source is connected to the vertical input of an oscilloscope when checking the RF envelope pattern of a transmitted signal? The local oscillator of the transmitter, an external RF oscillator, the transmitter balance mixer output, the attenuated RF output of the transmitter. Excuse me.
It should have an RF in the answer.
Yeah, the answer is delta on that one. You want to see the output of the transmitter. And to look at it, you have to attenuate it because you don't want to put 100 watts into your oscilloscope. Why do voltmeters have high input impedances? It improves the frequency response. It allows for higher voltages to be safely measured. It improves the resolution of the readings. It decreases the loading on circuits being measured.
You just talked about D.
Yeah, it's D. Whoops, I clicked it too many times, didn't I? But it is D. It used to be a lot harder. The old before they were solid state, the old meters usually only had about a 2000 K ohm. internal resistance. So it would affect the circuit quite a bit. What is the advantage of a digital voltmeter as compared to an analog voltmeter? Better for measuring computer circuits, less prone to overload, higher precision, faster response. Well, so a digital voltmeter, like it says, the meter is digital. And there's a clue. It's digital. So it'll give you,
Precise.
yeah, it's higher precision, Charlie. Instead of just trying to see if you have a needle, you know, is that needle on the 10 or is it on the 5? It looks like it's closer to 3. When is an analog multimeter preferred to a digital multimeter? When testing logic circuits, when high precision is desired, when measuring the frequency of an oscillator. Where did that come from? When adjusting circuits for maximum or minimum values. Well, you can eliminate these, right? It don't have much to do with logic. Like I said, it's not as high a precision as a digital one. It has nothing to do with frequency. So it must be D. And it is. You could see the needle bouncing. And
Is that related to when you're matching your antenna and you're looking at like a dual meter and you look at where the two needles meet?
no, that's power and SWR, or actually it's forward power and reverse power, those two, the cross needles. That's
But aren't you looking for the maximum SWR or the minimum one?
the minimum.
The
Yeah.
minimum.
But yeah, this is like if you're just looking at a voltmeter and the needle's shaking, you can see the higher and the lower values of the needle. I think that's what they're talking about.
Oh, okay.
Yeah. Because it doesn't have to do with frequency and
I've never used a digital one. I've only used the old school ones.
oh yeah. Oh wow. You have to buy one. They're real cheap now. The digital ones. Not that they're that great, but I which of the following can be determined with a directional watt meter? That's what you were talking about. Standing wave ratio, antenna front to back ratio, RF interference, radio wave propagation. Wow. Um,
SWR?
yeah, A. Yeah, that
Yeah, I was gonna say
yeah, that B there almost got me front to back, but that's talking about a
A.
Yagi where it throws more RF in one direction than the other. That's the front to back ratio. A it is. Which of the following must be connected to an antenna analyzer when it is being used for SWR measurements? Antenna analyzer, receiver, transmitter, antenna and feed line. Whoa! Me and my clicking. All these are correct. I'll tell you. So what should be connected?
Charlie, for
See,
sure.
Charlie. See,
Yeah, because this is the antenna analyzer, which has its own signal generator in it. So you don't want the transmitter. And it gives you a good, if you're doing it right, they work pretty good. There's a few things to watch. What effect can strong signals from nearby transmitters have on an antenna analyzer? Desensitization, which can cause intermodulation products, which interfere with impedance readings. Receive power that interferes with SWR readings. Generation of harmonics, which interfere with SWR readings. All these are correct, all these choices. Well, huh.
B.
Yeah, I'm thinking it's delta, so I'm guessing.
Oh,
No, receive power interferes with SWR.
yeah. All right.
There you go. Baker. Which is true. I guess all the rest were just gobbledygook. Which of the following can be measured with an antenna analyzer? Front to back ratio of an antenna, power output from a transmitter, impedance of coaxial cable, gain of directional antenna. Wow, which of the following can be measured with an antenna analyzer?
Charlie.
Charlie? That sounds pretty good. Yeah, because not it the rest of them refer to the antenna, don't they? It don't have anything to do with antenna gain or power output.
No.
All right, end of chapter 4. Good old Jerry. So, is anybody awake?
Yep.
Oh, oops, I did something wrong there. Hang on. Stop share. I don't want to share. There we
There
are.
we go. How about we take a break until 25 minutes past the hour?
5 minutes? Well,
No, 25 past the hour.
okay. It's 8:14.
Yeah, so stuff that is not, I have a quick little quiz here of stuff that's not on the exam, but goes over some of the decibel stuff again. And then once we're past that, I will take questions from the students. What you think you want to talk about, where you think you have weak points, it's up to you. And then if we have time, we can go through one of the online quizzes just on the chapter 4 stuff. So let's see here. I am going to try. Let's see if I can do this. This will only take a few minutes. Um, okay, where are we here? Oop, there we go. Let me share this. Okay, you should see a slide that says quick decibel review. So I got a series of 3 problems here. We'll start easy and work our way up a little bit. Excuse me, but if you get these, then you should have little problem with answering the questions on the test. So first is, Joe buys an amplifier to boost the power of his 5-watt transmitter to 100 watts. What is the gain of the amplifier in decibels? So I'm just going to go through the method here. The gain is equal to the power out divided by the power in, which is 100 divided by 5, or 20. And the gain in decibels is just 10 times the logarithm of that ratio. So, excuse me. So it's 10 times the logarithm of 100 over 5, or 10 times the logarithm of 20. And, whoop, did I get that wrong? No, yeah. So the logarithm of 20 is 1.3, so the gain is 13 dB. Now, one thing you should notice is, I think we talked about S units. S units are 6 decibels apart. So when you go from a very low powered rig to 100 watts, you're gaining about 2 S units. And then if you go from, say, 100 watts to 1500 watts, you're gaining a little bit less than 2 more S units. All things being equal, how strong the fella hears you at the other end.
What are you doing?
So Leslie is taking her daughter Caitlin to a pop concert. She buys earplugs that promise to reduce the outside noise by 95% to protect, well, her daughter's hearing and her own. So assuming that that number refers to noise power, by how many dB do Leslie's earplugs reduce the sound level from the band? And this goes back to some of the stuff that we talked about, small losses. So the gain is the power out over the power in, or in this case, it's attenuation or loss. But in is 100%, and what gets past the earplugs is 100 minus 95% or 5%. So the gain is 5% divided by 100% or 0.05. The gain in dB is 10 times the logarithm of 0.05 or minus 13 dB gain. And you notice this is just the inverse of the first problem. We went from 5 watts to 100 watts. We went from 100% of noise to 5% of noise. And the answer is the same, but with an opposite sign. So the gain of the earplugs is minus 13 dB, or the loss of the earplugs is 13 dB without the minus sign. So let's do one more here. So Joe transmits a 100-watt signal in Detroit, and Jane, who lives outstate, receives him with an S9 signal level. So at the antenna input of her receiver, Joe's signal is 50 microvolts. Assuming that assuming that the transmitter and receiver talk to 50 ohm impedance and ignoring antenna gain and any loss in cables, what is the path loss of the signal traveling between Joe and Jane? Now this is a tricky one, because notice that the transmit signal is in watts and the receive signal is in microvolts. So what you have to do first is change things to the same units of measure. So um, so if you decide to do things by power, then the transmitter is 100 watts. 50 microvolts into 50 ohms, power is equal to V squared over R. So it's 50 times 10 to the minus 6, that number squared, divided by 50. So you get 5 times 10 to the minus 11 watts. The voltage approach is 100 watts. To convert that to voltage, you take the square root of power times resistance, or the square root of 100 times 50. Square root of 5,000 is 70.7 volts, and 50 times 10 to the minus 6 volts is the same as 5 to the 10 minus 5. So that's the 50 microvolts. So now if you want to calculate that in decibels, let's go to the next slide here. I just threw these together. I'm sorry, they might be a little bit clearer if I did it more step by step. But so what we have here is a very small number of watts in the receiver, or um, a reasonable voltage at the transmitter and a very small voltage at the receiver. So if we do this looking at the relative power, then the gain in dB is the 10 times the log of the receive power over the transmit power. So that's 10 to the log of 5 to the minus 11th power divided by 100. And that works out to 5 times 10 to the minus 13th power. And so if you take the logarithm of that, you get minus 12.3. You multiply that by 10, and you get minus 123 dB. So the loss over that path is 123 dB, which is a huge amount. But it's also very typical. HF transceivers, most HF transceivers that you can buy run about 100 watts output. And an S9 signal is a fairly strong signal for amateur radio use. So The difference between those is over 120 decibels. And if you get a weaker signal, that loss number only goes up. So now let's do this in terms of voltage. It's 20 times. Now remember, for the gain, since we're measuring power, the gain is power ratio. The gain is 20 times the log of receive voltage over transmit voltage. So that's 20 times the log of 5 times 10 to the minus 5 divided by 70.7, which is about 7 times 10 to the minus 7th power, I guess. Yeah. And that logarithm is minus 6.15. Multiply that by 20. Again, you get minus 123 dB. So this is just walking through real quickly, but you can see that first of all, doing this problem two different ways, you can get the same answer, and it points out the importance of using the same units for everything. So now I'm not sure exactly what people want to do, but let me ask if people have questions on particular areas of chapter 4 that they'd like to talk about. So I'm going to ask here, the concepts that we have sort of zoomed our way through that, no pun intended, that just aren't clear to you.
The digital stuff, I'm just resigned to memorizing.
Okay. Any specific questions?
No,
Don,
Okay,
anything
there I am.
specific you'd like us to talk about?
Well, I'm just gonna do my best at memorizing, going over the materials and the questions and try to
Okay.
memorize.
How about Tony? I know you're playing catch up a little bit, but of the chapter 4 stuff, is there anything you'd like us to talk about specifically
No,
that
not
wasn't
really.
clear?
Some of it rings a little bit of a bell, but yeah, I'm going to end up trying to revert to my memory as long as I can not get that problem that the colonel's got at CRS. I have to watch out for that.
Okay. Frank, what about you? You have any questions about specific topics in chapter 4?
No, not really.
Okay. Well, then I'm going to spring this on you. We're going to try a practice test. I hope all you guys are doing practice tests on and off. Really, you should be doing them at least a few times a week at this point, and don't worry about crappy scores. The whole idea is to get the practice in. First of all, to familiarize yourself with the form of the test, and second of all, to get some rote learning by learning the correct answers to these. So let me do this. Let me share the screen again. So I'm going to share. I'm going to share this. Whoop, are people seeing? Yeah, are people seeing a thing that says general exam review?
RL exam
Yeah.
review.
Okay, good. Okay, so we are not going to do 65 questions. I think we're going to do about 15 or 20. So the first question is, what happens when inductive and capacitive reactance are equal in a series circuit? A, the resonance causes impedance to be very high. B, the impedance is equal to the geometric mean of the inductance and capacitance. C, resonance causes impedance to be very low. Or D, impedance is equal to the arithmetic mean of the inductance and capacitance.
Charlie,
Anybody else want to hazard a guess here?
Charlie.
Boy, we got silence at the other end here. Okay, Charlie. The answer is Charlie, yes. Um, now, inductive and capacitive reactance have opposite signs, so if they're equal, they cancel each other out. But that happens only complete cancellation happens only at one specific frequency, and the reactance of a series circuit, a series resonant circuit like that is low only over a fairly narrow band of frequencies. All right, so let's do this. What is reactance? Opposition to the flow of direct current caused by resistance, opposition to the flow of alternating current caused by capacitance or inductance, reinforcement of the flow of direct current, or reinforcement of the flow of alternating current.
Bravo.
Okay. Any other guesses? There's three others of you. Speak up.
Well, you know it's AC.
Yep. Well, the answer is bravo. Yes. Which of the following is opposition to the flow of alternating current in an inductor? A, conductance, B, reluctance, C, admittance, or D, reactance?
Reactance again.
Definitely
Yep.
D.
Yeah, it's D. It has to be D. Those other three are valid terms, but we haven't really talked about them. Which of the following is opposition to the flow of alternating current in a capacitor? And you have the same choices in a slightly different order.
Got to be reactance again.
Yep, the answer is reactance again.
Gotta love the
How
way they
does
try.
Sorry?
Gotta love the way they try to confuse you.
Yeah, well, multiple choice exam takes you right back to high school, I think. Um, how does an inductor react to AC? As the frequency of the applied AC increases, the reactance decreases. As the amplitude increases, the reactance increases. As the amplitude increases, the reactance decreases. As the frequency of the applied AC increases, the reactance increases. These are inductors, coils.
Ooh. It's either A or D.
Yup.
I'm thinking D. I could be wrong.
Yep, the answer is indeed D. Yeah, so as frequency increases, the inductance, the reactance, excuse me, of an inductor increases. So um, so coils do better at blocking higher frequencies. How does a capacitor react to AC? As the frequency of the applied AC increases, the reactance decreases. As the frequency increases, the reactance increases. As the amplitude increases, the reactance increases. As the amplitude increases, the reactance decreases.
It's the opposite of the one before. Got to be A.
Yep, that's exactly it. A, alpha. Yep, so, excuse me, so if inductors are better at blocking higher frequencies, capacitors are better at blocking lower frequencies. And specifically, a capacitor should block all of DC current. What is the term for the inverse of impedance? Conductance, susceptance, reluctance, or admittance?
Susceptance. That's funny. Admittance, wasn't it?
Let's take a look. Yep, admittance. Conductance is the opposite, is the inverse of resistance. But admittance is the inverse of impedance.
Well, I got that one wrong.
What is impedance? The ratio of current to voltage, the product of current and voltage, the ratio of voltage to current, or the product of current and reactance. And I'll give you a hint, this goes back to Ohm's law.
V divided by R.
Yep. So which choice is that?
V divided by V divided by R. V divided by R.
Okay,
None of those are V
let
divided
me
by R.
help out on this one. Resistance is the same as R in Ohm's law.
So it'd be V divided by R, but none of those are V divided by R, are they?
Yeah,
No,
this one, C, Charlie, the ratio of voltage to current, which is another way of saying voltage divided by current.
Oh, I is R. I'm thinking I is current. Yeah, I'm thinking of Ohm's law.
Yeah, you should be thinking of Ohm's law.
No, but I was thinking I was current.
Yeah, I is current. So R equals V over I, or E over I, depending on how you which symbol you use.
Yeah, I was just thinking I was current
Okay.
instead of impedance.
What unit is used to measure reactance? Farads, ohms, amperes, or Siemens?
It's ohms.
Yeah, I was going to say ohms.
Yeah, it's ohms. That's right. Which of the following devices can be used for impedance matching at radio frequencies? A, a transformer, B, a pi network, C, a length of transmission line, or D, all of the above?
Definitely C.
Delta.
Yep, the answer is D. All of these choices are correct. Um, excuse me. Uh, a transformer, the impedance ratio on the two sides of the transformer are the square of the turns ratio. In a pi network, you can transform pretty much any impedance into another impedance, and pi networks are used um, in for things like antenna tuners. Um, and so that whatever the impedance of the antenna is, you can match to 50 ohms at the transmitter output. A length of transmission line, if the characteristic impedance of a transmission line is different from the impedance at one end than the impedance at the other end, um, will will look different unless the transmission line is electrically some multiple of 1/2 wavelength. But transmission lines that are not matched to the impedance at one end can be used to transform that to the impedance at to a different impedance at the other end. And as a matter of fact, if you have a random length of coax coming from your antenna to your radio, and the antenna is not an exact match, then the um, then the impedance that the transmitter sees will also not be an exact match to the cable. Unless again, you happen to hit right on a multiple of 1/2 wavelength. Okay, we're not going to go very much longer. What letter is used to represent reactance? Z, X, B, or Y?
It's either A or B.
Okay. Any guesses?
Bravo.
Yep, the answer is X for reactance. Z is impedance, Y is the inverse, admittance. I've forgotten what that is.
Baloney.
No. It does stand for a measure of something. I'm sorry, but It's something we didn't cover. That's my official answer. What occurs in an LC circuit at resonance? A, the current and voltage are equal. B, resistance is canceled. C, the circuit radiates all its energy in the form of radio waves. Or D, inductive reactance and capacitive reactance cancel.
Delta.
Yep, D. That's right. That means yeah, a resonant circuit. A resonant circuit, if an inductor and capacitor are in series, it acts like a short circuit, and if they're in parallel, it acts like an open circuit at the resonant frequency, but not at other frequencies. What dB change represents a factor of 2 increase or decrease in power? 2 dB, 3, 6, or 9 dB?
That's the log of 2 times 10. Has to be 3.
Yep, there you go. 3 dB. 3 dB means means the power ratio is either double or half. B equals susceptance, says our silent host, Bob.
Susceptance? What is that?
Susceptance. So
What is
that's the
that?
opposite. That's the inverse of reactance. That is something you do not have to know for
Previous,
Oh boy, that's a
for
new
the
one.
sake of this.
previous question, not this one.
Yeah. How does the total current relate to the individual currents in a circuit of parallel resistors? A, the total current equals the average of the branch currents. B, it decreases as more parallel branches are added to the circuit. C, it equals the sum of the currents through each branch. Or D, it is the sum of the reciprocal of each individual voltage drop.
I think it's D, delta.
Any other guesses?
Huh.
It's either
Well,
the sum or the reciprocals, either C
nope.
or D.
D is wrong. It is the total current in the circuit is equal to the sum of the currents in each branch.
That's
Oh, voltage. Yeah, it's the
parallel
opposite.
circuit,
Yeah.
parallel circuit.
Yeah, so okay. The sum of reciprocals things is for adding um, resistors or inductors in parallel or capacitors in series to get the equivalent value. All right, how many watts of electrical power are consumed if 400 volts DC is supplied to an 800 ohm load? Half a watt, 200, 400, or 3,200 watts?
I squared.
Guess is Bravo.
Okay, the formula here is power equals V squared over R. So it's 400 squared divided by 800. So you think 200 watts? Let's find out. Yes, that's excellent. All right, I'm going to do 5 more and then we'll quit for the night. How many watts of electrical power are consumed by a 12 volt DC light bulb that draws 0.2 amperes? 2.4 watts, 24, 6, or 60 watts?
Hmm. Oh,
Guesses?
Yeah.
Sorry?
Me, 2.4.
Yeah. A.
2.4, yeah, A, that's right, 2.4. It's power equals V times I. How many watts are consumed when a current of 7 milliamperes flows through a 1250 ohm resistance? A, 61 milliwatts, B, 61 watts, C, 11 milliwatts, or D, 11 watts.
Where's that calculator?
61?
Okay, 61 what?
Yeah, it is.
Milliwatts or watts?
Watts.
Yeah.
Is that the consensus? Okay. No, the answer is 61 milliwatts.
Oh, because it's milliamperes.
Yeah, it's milliamperes. So
Yeah, okay,
that's
so I
so
got,
7
yeah,
milliamperes is 0.007 amps. So you have to take that into account.
getting tired. I'm getting sleepy.
I
Okay,
squared.
well, we got 3 more to go and then we'll call it a night.
I squared.
What is the PEP produced by 200 volts peak to peak across a 50 ohm dummy load? 1.4 watts, 100 watts, 353.5 watts, or 400 watts? Now, this is kind of a trick question
Oh,
because you have
point
to convert
seven
the
is in
peak to peak
there.
voltage to something else.
200 times point 0.7.
100 times point. So, because it's peak to peak.
I guess
That'd
delta.
be 100 watts probably.
Well, the answer here is 100 watts. Let me walk you through that. 200 volts peak to peak, that's the maximum positive voltage and the maximum negative voltage, is 100 volts peak voltage, which is from the maximum voltage to zero. But to calculate PEP, you need the RMS voltage. And here we're just going to assume it's a sine wave. And we're going to assume that we're dealing with a sine wave and say the RMS voltage is point 7 times the 0.7 times the peak voltage. So that's about 70 volts. So that's 4,900 and some pardon me. Power is V squared over R, so that's 70 times 70 divided by 50, or about 4,900 divided by 50, which is 100 watts. Just waving my hands a little bit. It's actually, I believe, 70.7 volts if you multiply it out the right with enough precision. What value of an AC signal produces the same power dissipation in a resistor as a DC voltage of the same value? A, the peak to peak value, B, the peak value, C, the RMS value, or D, the reciprocal of the RMS value. What AC voltage produces the same power dissipation in a resistor as a DC voltage of the same value?
C.
Okay.
Yeah, it's C, the RMS value. So the usefulness of the RMS value is it tells you how much power is dissipated. Um, even though the relationship to the actual peak voltage or average voltage or what have you in a signal may be complicated. What is the peak-to-peak voltage of a sine wave with RMS voltage of 120 volts? A, 84.8, B, 169.7, C, 240, or D, 339.4 volts? So you want to get peak to peak from RMS. So what do?
1.414 times the voltage, RMS.
And what does that get you, Colonel?
168.
Okay. All right. Well, this is another two-step problem. So I see a little bewilderment here. So if we guess 169 point something, that's incorrect. So to get
One,
from peak to get
oh,
from
peak to
RMS
peak,
to
peak to
peak to
peak,
peak,
not RMS. Yeah.
yeah, it's
Yes.
two steps here. You convert from RMS to peak voltage and then double that to get peak to peak voltage.
Yeah. I didn't get the peak to peak. Sorry about that.
Yep, no, that's okay. So that is about 1/3 of the chapter 4 questions. So I see that people are still kind of what's going on here?
Gotta memorize those equations.
Yeah, you do, you really do. So I'm going to send out a handout to help, a couple of handouts to help with that very shortly. And also, for what it's worth, all of the previous weeks um, of videos of this class are up on YouTube now, and I'll send a message with the links to all of those. It's a little bit disorganized, but that's okay. You can find them all pretty easily. And I hope that everybody is taking the practice tests. As I said before, no matter how terrible you do right now, it really helps a lot to take those regularly. And if you haven't settled on one particular brand, if you like, I'd say try all 3 or 4 that are in the handout that I sent out at the beginning of the course. And I think the cat's going to continue to ignore us there. So that's all for tonight. Next week, Marv, if he's feeling up to it, is going to talk about antennas, which is chapter
What are you doing?
chapter 7. Talk about antennas and feed lines. So read up on chapter 7, and let's hope that the surgeon did a good job on Marv. And I hope to see all of you next week.
Yep.
Yep. And we will be at least momentarily back on schedule.
Good night, everybody.
All right. Good night. Good night, all.
Good night, 73s.